In today's tutorial, I'm going to give you 3 design tips to improve your CNC milled parts. So let's jump over to Fusion and go through it. Tip number 1 is that you want to slightly oversize the radius of your internal fillets or your internal corners. So the reason for this is your cutter, what you will be using to actually mill this pocket out, has a fixed radius or a fixed diameter. And in this case, our pocket is 1.5 inches deep, and I have it modeled with a 0.25 inch radius. That means you could cut this pocket out with a cutter that is a 1/2 inch in diameter or a 1/4 inch radius. But if you did that and you look at this from the top, the radius will exactly match your cutter. So as your cutter comes along, it's going to get to the corner, it's going to have to stop and make a right angle and come down to keep cutting. And it's going to have to do that at each corner. Now, why is that a problem? You might think, well, that's fine. Our fillet is a 1/4 inch. The radius of our tool is a 1/4 inch, no problem. Well, there's a few issues with that. When your tool comes over and stops and has to change directions at 90 degrees, you're going to engage more material at that moment you come into this corner. It may slightly oversize your fillet or the radius in this corner, so you might be out of tolerance, and your surface finish will not be quite as nice as the tool is engaging with more material at once. So those can cause problems. Those can cause quality issues. So what you want to do is actually slightly oversize this radius based on what tool size you think will actually be used to cut this out. So let's talk a little bit more about the tool. If we go over to McMaster, here's a tool that could be used to cut this out. You can see it has a 1/2 inch diameter, so a 1/4 inch radius. And this is something that would work pretty well. It has a cutting depth or a length of cut of 1.5 inches. You can see that here. So this tool is something that could work. But you might notice that it also has a radius on the bottom of it. And that is something that I can show you here in a minute, the impact that will have and why you may want that. Other ones you get can just have a square end. And there just be a square end mill. This one has a rounded edge, which is just dependent on what you want your pocket to look like. But here, so you see the diameter is a 1/2 inch exactly, plus 0 minus, 1.5 thou. So essentially exactly a 1/2 inch. So we want to oversize this a little bit so we don't have this issue of the tool coming and stopping in the corner and then turning 90 degrees. You want it to be a nice, smooth cut. So to do that, let's oversize this. So we'll go back into our fillet, and instead of a 1/4 inch, let's bump that up to 0.3 inches. And so now, since it's oversized, the cutter can essentially follow the path of this wall or this edge without having to stop and make a 90-degree turn. To kind of drive this point home, I'm going to switch over to the camera real quick and just use this marker as an example. So you think about if your fillet radius is exactly the radius of your cutter, it's going to look something like this. It's going to come over, stop, down, stop, over, stop. It'll be very quick. It'll look, something like that. But those little moments of stopping, like I said, may cause quality issues and may cause some issues with things like tolerancing or surface finish. But after we've oversized it from a 1/4 inch to 0.3, your tool's going to look a little bit more like this, where it's going to come, sweep a corner, come down, sweep a corner, come over, sweep the corner. And you'll get a much nicer finish, and you're more likely to actually hit your tolerances, which is a big deal. This is something that will make you happier as the designer of the part. It'll make your quality team happier and may even make your machinist a bit happier. One reason why it may make your machinist happier is if you model this at exactly a 1/4 inch, they would probably know this issue and they would automatically default to a smaller cutter so that they didn't exactly match the radius of the fillet with the radius of the cutter. And the downside of this is if they use a smaller cutter, it's just going to take longer to actually mill out this pocket, and they will pass that cost on to you, the designer, or the company that is ordering these parts. So that's not ideal, especially if you are trying to maximize or optimize the cost of your part. So again, just to review that, you want to slightly oversize the radius for your internal corners. And that is oversized based on the radius of the cutter that you believe will be used to actually mill out your part. Now, the next tip is looking at the ratio between the radius or the diameter of the the tool that will be used to mill out this pocket and the depth of your pocket. And now let's try to think about why that matters. So you're looking at this depth here, and then you're also looking at the radius here. So if we reduce this radius, just as an example, let's say we reduce it from 0.3 to 0.13. Now you're going to have to use a much smaller cutter to mill out this pocket. If it's 0.13, you're going to have to use something that is probably a 1/4 inch end mill because the diameter is 0.25. This radius is 0.13, so a diameter of 0.26 if you double that. And that will require you to have a much longer end mill to make this cut. Now, why does this matter? Well, again, let's go over to the camera real quick, and I will show you just a quick example of why this may matter. So if you think about it, if you have a larger cutter, you can hold it a little bit closer to where it's actually going to be cutting. Let's say this is your material and this is your end mill. So it's going to come and cut, and you're going to get a nice, you'll have a nice stiff tool, and you're going to get a nice surface finish on the surfaces that you're cutting. However, if you have a smaller internal radius, then you're going to have a longer tool, and it's going to be held more kind of like this. Just imagine this is a smaller diameter cutter that you'll be using to mill that out. And as you come in to cut your edge, you can see this thing is just not going to be as stiff. So you're going to get some deflection, you're going to get some chatter as it goes along and cuts the edge of that part. And so you're going to have a worse surface finish, potentially not hit your tolerances, and is going to be a more difficult part for the machinist to make, and they are going to charge you more for that. So, what is the tip? How should you design this? Well, a good rule of thumb is going for a ratio of 3:1. And this is a ratio of the depth of your cut to the diameter of your cutter, or the cutter that you think will be used to mill out your pocket. So, in this case, let's see, the depth of it here is, well, let's pull up our measurement tool. Okay, depth, as I said, is 1.5 inches. So we want a 3:1 ratio. So 1.5 divided by 3, you probably already did it in your head, that's a 1/2 inch. So that means the diameter of our tool or our cutter should be a 1/2 inch. Okay, so what does that mean for the radius? Well, that means we should go back to where it was. And we should, let's make sure to close that. Let's go back to 0.25, or as we discussed, something that's slightly oversized. So we'll go to 0.3. This way, you know that you're going to have a nice stiff tool as it's going through and making this cut and milling out this pocket. You're going to have a better chance of hitting your tolerances, and you'll also have a better surface finish on these internal surfaces. Additionally, the cost will be reflected as lower if you do this, and there's a few reasons for that. The first one is, again, if you have a larger cutter, you're just going to be able to cut out this pocket faster. And that's just kind of common sense. If you are using a larger shovel, you can dig a hole a lot faster than if you're digging with a tiny shovel, right? And it's kind of similar here. If you're using a larger tool, you're going to be able to remove more material faster. But if you reduce your internal fillet here, let's go back to that 0.13. Now you have to use a much smaller tool to mill this out, or you have to use two different tools. You could use a larger one to mill out most of it, and then use a smaller tool to finish it and get these 0.13-inch radius corners or fillets on your internal corners. And so then you have an extra tool change, and that is also going to add some cost to your part. And then you can imagine if you make this even smaller, let's say we go 0.063, now this is just a plain difficult part to use or to manufacture, because you're going to have to use a cutter that is very thin, has a very small diameter, and it's going to have to cut a very long distance, 1.5 inches down. So that is going to wobble, that is going to chatter, it's going to mess up your surface finish. And that's if you can even source a tool that has that diameter as well as that length of cut. And again, going back to McMaster-Carr, you can search for that if you want. If you're designing a part and you want to see, is this even manufacturable? Let's go away from the 1/2 inch milling diameter. And in this case, we were talking about a 1/16 inch. Okay. We don't necessarily need the rounded edge at the bottom of this tool. Let's get rid of that. And we want to look at the length of cut. So here, at least on McMaster, the longest length of cut you can get on something that is a 1/16 inch diameter is only 1 inch. And let's just look at that. And this is also tapered. So again, this is just a way to see that this is probably going to be a difficult part. Not to say that it's impossible, but you're definitely not making it easy on your machinist, and you are going to see that reflected in the cost. So that's a helpful tool there. It's not one of the 3 primary tips, but make sure that the part you're manufacturing actually has, there's available tools to even be able to manufacture it. So you want to make sure you stick to that 3-to-1 ratio. And again, that's the ratio between the diameter of the cutting tool to the depth of your pocket. You might be able to get away with a 6-to-1 ratio. You can get away with higher, 9-to-1, 10-to-1, but you will start to see some cost impacts on that. And I did a quick little test of this just to see what a online shop would quote. And of course, I went with Send Cut Send because they're awesome. And I did a few tests with this. And let's just see what the price difference is. So here's a square piece with a 1.5 inch cut in it as well, with some different radii, with a 3-to-1 ratio, 6-to-1 ratio, and a 10-to-1 ratio. You can see in this case, the pricing actually doesn't really change that much. And I think the reason for that is it's a smaller part. The time in the machine to actually mill out this pocket doesn't really change much from using a larger end mill up here to a smaller end mill when you have that 10-to-1 ratio. However, as you get to larger parts where there's a lot more material to remove, you start to see more of a difference. So if you use the 3-to-1 ratio, you can see this part is $595. If you go to 6-to-1, it goes up to $597. 10-to-1, it goes to $598. Again, in this case, these prices are all very similar, but you can see the trend. As they're having to use a smaller cutter, it's going to take longer to remove all of that material, or they have to do a tool change, which also adds cost. So that's just a quick example of why this ratio is pretty important and matters, especially you can imagine if you are manufacturing a bunch of these parts and maybe even just a small cost difference starts to add up over time. So I had mentioned it a minute ago before we get to our third design tip. I had mentioned that you can get these cutters that have a fillet at the bottom. So let's see what that would look like on one of these parts. I want to change this back to, let's go back to 0.3. We have a decent fillet here, decent radius to work with. And then let's go back over to McMaster, and we'll back up a little bit. Instead of a 16th inch, we'll go back to our 1/2 inch. And we want not the ball end mill, but we want to use this round edge, this rounded edge end mill. So let's scroll through here. Let's find one with a 1.5 inch cut. Okay. Now if we make this a bit larger, you can see there's a radius at the bottom of your cutter. So instead of having the sharp corner, you can actually have a radius or a fillet at the bottom of your pocket. And depending on your design constraints, what this is being used for, you may want this. So let's just model that in very quickly. We'll click here, 0.125. And there, you can see we have added that fillet at the bottom of the pocket. So again, go to McMaster, look at the different tools. There's other websites too that you can reference if you need more exotic tools, but McMaster is usually a really good place to start. Okay, the third and final design tip that will make you a CNC mill design pro. I don't think that is probably the right wording for that, but will make you more of a pro when you're designing parts that will be manufactured with CNC milling. And this has to do with tapped holes. So let's add a few tapped holes on this part. Okay, we'll create a sketch on this top plane. Rectangle, we'll start in the center here. Bring it out. And the distance from the edge. Let's see. Oh, and I got a low battery signal on my laptop. So let me plug that in real quick. All right, crisis averted. Let's keep going with this tutorial. Let's make this 0.25 from the edge. We'll make this one 0.25 from the edge, okay. And that'll be our sketch. This will tell us where we want to put our tapped holes. And we'll come up here to the hole tool. Okay, select multiple. Wow, look at the default there, those are giant. Not what we want, but let's adjust those. So the extent, well, first let's give you the tip. So the tip here is you don't want to, by default, add a threaded hole that just goes all the way through your part and is threaded all the way through, especially if you have a thicker part, like the one we have right here, which is 2 inches thick. The reason for that is having to tap this all the way through, there's a lot of threads that you will need to add, and it's going to build up a lot of friction. And depending on the material that you're working with, you may actually break your tap, and that will cause lots of headaches for your machinist and headaches and money for you. So let's design this, or let's actually select a tapped hole that fits in these locations. So let's see, let's come down here. We want metric, okay. Let's see, what size do we want? Let's make it 4 millimeters. We have an M4. Actually, let's bump that up just a touch more. Let's go to 6. Okay, and you might be tempted at the start, like I mentioned, to just say, well, I just want a tapped hole. It's going to go all the way through. Yep, we'll set it to tapped here, and we just want it to be full. Hit OK. And wow, look at that. We have this tapped hole that goes all the way through our part. You can thread it from either side. It's very usable, right? Well, no, not necessarily. This could be a huge problem to manufacture. Having to tap this all the way through, especially if you're working with a common material like a 300 series stainless steel, maybe if you're working with titanium or just a hardened steel in general, trying to tap a hole like this is going to be an absolute nightmare. And you'll probably just get either a no quote or they'll push back on you and say, hey, we can't tap this all the way through, unless they're able to use something like a thread mill to cut the threads. But even that is going to be difficult on a part this thick with this small of a tapped hole. So what's the solution? Well, in general, you don't need a tapped hole to be tapped all the way through. You really, to get the full strength of that tapped hole when you're threading a screw in, you probably only need 1 to 1.5 times the diameter of that screw in length. So for example, this is for an M6. You will only need 6 millimeters of threads, or maybe, up to 9, maybe 12, maybe 2 times the diameter of the thread itself. So let's go back into our hole tool and update this. So we'll come up here, instead of going all the way through, we'll make it a distance, okay? And for the thread offset, we're not gonna have it full, but we will have an actual offset. And then the depth of the drill, let's just change that to 1.5. Oh, and I hit enter and close it. So let's open that up one more time. Okay, so we're drilling 1.5 inches deep there. But we only need, like I said, about 12 millimeters maximum of threads. So here you can come in, and this is your thread depth. So they'll drill it out, and then they'll come in and actually tap it. And that's where they add the threads to your part. So let's test this out. Let's see, can I mix up units here? 12 millimeters. And it looks like I can. Okay. And so now let's take a look at this. Let's do some inspection. We'll do a section analysis, so we can actually look at a section of this thread. Okay. And as you can see, we probably drilled this too deep as well. Honestly, you don't need it a whole lot deeper, probably 2 to 3 thread pitches deeper than where your threads end. But you can see it's only threaded down 12 millimeters. This is going to be so much easier for a machinist to actually make for you. This is going to be so much easier to manufacture. The odds of breaking a tap in this are much, much lower. And so this will make your machinist happy, and happy machinists make good parts. In general, that is mostly true. And what I mean by that is if you design your parts well and make parts that the machinist doesn't necessarily have to worry about, try anything crazy, if they're not breaking taps, if they're not having a hard time hitting your tolerances, they're going to be much happier, and you are going to get better parts. So that is it. Let's turn off this analysis. So this is the part. We have this milled pocket, and I went through and told you about the importance of oversizing just slightly your internal corners, your internal fillets. Make sure you oversize them just slightly over the radius of the tool or the cutter that will be milling out these pockets. That will allow you to have better tolerances and better surface finishes. Also, make sure that the ratio between the diameter of your cutter and the depth of your cut is around 3 to 1. Maybe bump it up to 6 to 1 depending on your design. But that 3 to 1 ratio is going to be kind of your Goldilocks zone. That's where you're going to want to be. And then finally, for tapped holes, especially when you're adding tapped holes in something like stainless steel or titanium, make sure that the depth of the thread portion itself is somewhere between 1.5 to 2 times the diameter of the thread. So again, in this case, it's a 6 millimeter or an M6 thread. So 6 millimeters, multiply that by 2. And so you can have a threaded depth of 12 millimeters, and you will have a good part. Okay, so those are a lot of tips, but they are going to, well, 3 tips, a lot of details. And those are going to improve your parts. They are going to make them more manufacturable. If you are someone who is just getting started with fusion, maybe just getting started in mechanical engineering, these are tips that you need to memorize and just inherently have in everything you design. So that's it for this tutorial. As always, thank you so much for watching, and make sure you subscribe and stay tuned for more tutorials coming out soon.